So here is Unit 3. This is our Polynomials unit. So our very first outcome is taking a look at what are polynomials to begin with. And we're going to be discussing what they are, how to model them, how to draw them, how to write them in numbers with letters, and we're also going to learn all the different definitions. So that's our first section. First section is definitions. So when we look at things, the first definition here is talking about algebra tiles. So if you remember algebra tiles from last year, algebra tiles are pictures of things. So they are either little squares, triangles, circles, rectangles. So they're little objects that are representing a whole, okay? So you've got little units, single units, and then you've got long rectangles, which is your variables. Okay, that's a single variable. Then we've got squares, circles. Big squared is a variable squared. We're going to split all those equal. Number 2, the second definition, is called coefficients. Coefficient is a number that's going to come in front of or sit in front of a variable. Okay? So another word for it, they call it the numerical factor, but we're going to make that in our own words. What that actually means is that a number in front of a variable. Okay, that's all it means, is a number in front of a variable. Now, if there's no number in front, there might be one underneath. That's still a coefficient, okay, because they're attached side by side or top to bottom, okay? So that's what a coefficient is. Then we look at what a variable is. So variables are just numbers or letters, just variables are letters or symbols that represent unknowns. So we have the symbol pi, and pi represents an unknown amount. Well, we know an approximate amount, but we don't know the full amount because it's a run-on irrational number. So we know it's around 3.14, but it goes on forever, okay? So pi they use as a symbol for that then, because we can't write every decimal place on pi. So we're just going to be writing basically the digit pi, or the symbol pi. Another variable are any of the letters A through Z, okay? Typically we use a lot of X's and we use a lot of Y's. We try not to use the letter T because it looks like a plus sign, but they will be used here and there. Now, how to identify a term? So a term is when you've got variables and numbers stuck together. That's a term, okay? So, variables and numbers stuck together. Because if they're stuck together, that means they're side by side. And if they're side by side, sticking together like that, that means multiply. Okay? So, we all know from Unit 1, which was our exponents unit, we know all about exponents on letters and numbers. Now, each one of these is considered a term. They are all different types of terms. This first one doesn't have any variables at all. So we're actually going to call him a constant term. So that's what we call a constant. The constant, I call him constantly lonely. He's lonely because he's all by himself. He doesn't have a variable. Okay? So they are lonely. They have no variables. Then we've got the other terms that do have variables attached. So they could have a positive variable, a negative, so a positive coefficient, a negative coefficient. They could have 2 letters stuck together, that's okay. They could have a bunch of letters stuck together, and that's okay. All right? So, whenever we're just talking about a digit by itself, though, we only refer to it as a constant term. Okay? So, we get into a couple different specific definitions. We talked about sizes of polynomials. So now we're going to get into the next set of definitions. So these are the different sizes of polynomials. So the first one you see there is a monomial. What do you think the prefix mono means? 1. Good. So mono, for a monomial, is one term only. So that's what they are. They are one term only. Now, monomials, they can be created with fractions, and they're typically created with fractions. So monomials have letters and variables and numbers stuck beside them on top or on the bottom of a fraction. So every single one of these are monomials, okay? We've got y squared here. Now, whenever it's written as a fraction like that, the variable is going to float to the top number, okay, whenever we've got a fraction. So if they write 4 over 5 w cubed, what that actually means is 4w cubed over 5, okay? That's what it means. The w will go with the top one, okay? So, -4, what kind of term is that one? Starts with a C. It's a constant. He's lonely. He doesn't have a variable at all. 2x, he's got a variable and a coefficient. Okay, so he's one term by himself. Now we're talking about non-monomials. These non-monomials are actually non-polynomials. They're non-polys. And there's a reason that they're not a polynomial. Okay? So there's 3 things that cannot be polynomials. First thing that can't be a polynomial, that goes with the first example here. What do you see that it looks like? What do you think I can't name it a polynomial the first reason? Any wild guesses? Look at where everything's situated. What do you think? Any wild guesses? It's actually the opposite, because the variable's at the bottom. So, when there's a variable on the bottom of the fraction, we know it exists. We've been dealing with that stuff all of Unit 1 and some of Unit 2. We know they exist, but they don't get the special name polynomial. So, variables on bottom of a fraction. So that's the first thing that cannot be given the special name of polynomial. What do you notice about the second one? What's the second example? What do you notice about the second example? Anybody?
No numbers.
It's what?
No numbers.
There's no numbers. But what do you see? A square root sign. And with no numbers and only variables, we can only have, under a root sign, we can only have a variable that has an even exponent. So, for this example, the second thing is variables with odd number exponents under root signs. And I spelled under wrong. Under. With just an R. Okay, so variables with odd number exponents under the root sign. What kind of an exponent does that x have? It's got that hidden 1 on it, and 1 is an odd number. So if it has a 1 or a 3 or a 5 under a root sign, it can't be called a polynomial. Do they exist? You bet. We call them radicals. Okay? They're not called polynomials. They just get a different name. Nope, not to break time. The only radicals we were dealing with are not with variables underneath. So the radicals we dealt with were perfect squares and non-perfect squares. Okay, those are still radicals. Okay, the third example. What do you notice about the exponent? In the third example, what do you notice? It starts with an F. Fraction. So, no fraction exponents. Okay, no fraction exponents. And then again, that's to be given the special name of polynomial. All of these exist. They're just not given the name polynomial. So that's number 3. So there's 3 things that are not polynomials. All right. Then they do give us the general definition of a polynomial. So it says, a polynomial is a monomial or a combination of sums or differences, meaning adding or subtracting, different monomials. So basically what they are is a whole bunch of monomials with plus and subtract signs between them. That's all they are. Okay? So here's a polynomial, the very first one. Wrong one, there we go. It's just 3x. 3 and x stuck together by itself. So that is a monomial. If I separate, the next one is 2x subtract 1. How many terms are in that second one? 2 terms, good. So terms, the thing we have to remember about terms, we're going to write this up besides, we have it here, on number 4. Okay, we're going to go to our term definition. I want you to add something to the term definition. Terms are separated by plus and subtract signs. So that's a huge thing for terms. They are separated by plus and subtract signs. That's how we're able to count how many we have. Okay? They're always separated by a plus or subtract sign. So that's going to help us when we talk about the next few. So, looking at these guys, this guy has 1 term, this guy has 2 terms. How many does this one have? 3 terms, good. You're just counting how many things are separated by a plus or subtract thing, okay? So, plus or subtract signs, that is. Now, a 1 term is called a monomial. If I were to replace that prefix, mono, I could change it into a 2 term. What would I change mono to mean 2 terms? What do you think? What is a prefix that means 2? What do you think? Bi. So, binomial. Okay? Bicycle. You're writing a bicycle, B-I, 2 tires. Tricycle, 3 tires, 3 wheels. Okay? So, 2 terms is called a binomial. And 3 terms is specifically called a trinomial. So we have 3 specific names. We have monomials, 1 term, binomials, and trinomials. Okay? And polynomials are made up of a whole bunch of monomials added and subtracted together. Okay? That's all they are. So if we have any big long sentence that has a whole bunch of terms in it, if it's got any more than 3 terms, we just call it a polynomial. So let's say it has 5 terms in it. We could say it is a polynomial, or we could specifically call it a 5-term polynomial. Okay, if it's 4 terms, 4-term polynomial. Or you could just call it a polynomial. Because poly, the prefix poly means many. Okay? So, poly is many. So, however many terms we have, we could talk about, in general, a polynomial. Now we're talking about the degree. So this first little bit's a whole bunch of definitions. We're going to put it in a chart and see what it looks like. So, degree is the leading term of a polynomial. So, the degree. The degree is the largest exponent on the variable, or the sum of the exponents of variables that are connected. So the variables that are connected you can add together. So I'm going to show you examples of that. So here, this would be a positive 2, that's a negative 1. Okay? So it's plus a negative 1 or just minus 1. Okay? Okay, so now on degree. If we were to talk about the different types of degrees we have. So if I have, let's say, example, 4x, 3y, 2 minus 5, z, 6y, plus 4w squared x. All right. All we're going to do for an example like this is we're going to see how many variables are stuck together. These guys have a whole bunch of variables stuck together. So I've got x, y stuck together here. I've got YZ stuck together here, and I've got WX stuck together there. So, first of all, we want to see if any of them match. Do any of those variables match identically? If they're going to match identically, what that means is they have to have the identical same numbers and same variables. So if I wanted to match something to this 4, it would have to have an x3, y2 with it. Okay? So that's the only thing I can match to this guy. So when I look at those other ones, they're not the same. They have different variables, different exponents, so they don't match. Okay? Now, when you've got combined exponents or combined variables like that, you have to add the exponents and the variables. So these guys are going to give me a total of 5. These guys here are going to give me a total of 7, because don't forget you have a hidden 1 on that y. And over here we have a hidden 1 on the x. And over here we have a total of 3. So we always name our polynomial by the degree of the largest. So the largest degree here would be 7. This guy would be a degree 7. Okay? So 7 is the largest. Okay? So he is a degree 7. Now, if it wants the leading term is going to be the guy with the leading, the highest degree on it. Now, we call this the leading coefficient of the term. The leading coefficient is the number in front of that term. So in this case, a leading coefficient of our leading term is going to be -5. Okay? So -5 is the leading coefficient. And don't forget, coefficient just means a number in front of a variable. If I'm writing this stuff down, you guys, that means you have to write it down too. Don't just be sitting there staring at it. It's not going to magically appear on your page. If you're not going to write it down now, you'll have to be in at lunch writing it down. I have no problem with that. So, we have a whole bunch of definitions. Our degree talks about the largest exponent on the sum of polynomials of variables. But it's only if they're connected together. I'm not going to add this guy over here, the 4x cubed y2. I'm not going to add 5 to that 7. I'm not going to do that because they're separated by a subtract sign. These guys over here are separated by a plus sign. I'm not going to add their exponents to these guys. Okay? Again, this is just for naming degree of a polynomial. Okay? So, degree in first term, that is. So let's take a look at what each of these would reference. So, here is our first polynomial. Okay? We want to break it down into the number of terms. First of all, how many terms does it have? What do you think? How many things are separated if you were to count the separations? 3. Okay. What do we call 3-term polynomials? Trinomial. Good. So we have a trinomial. And now we have to add the exponents. Now, do we have any that are variables are bunched together? We have variables bunched together in the first term? No, different variables, just x's. What about the middle one? Just x's. And what about the last guy? Just a 4. He's a constant. He's lonely. Okay, so we're looking at the terms. We've identified 3 separate terms. Now we want to do the degree. What is the degree of the first term here? 2, because of the 2 on the x. Why do they have a 1 here? That's right. The x has an invisible 1. Now, why did they put a 0 with that guy? Any guesses? Because he's a constant is the correct answer. But the 0 stands for 0 variables. So, if this guy has 0 variables, that means he has a 0 degree. Okay? You have to have a variable to have a degree. Okay? So constants are always considered degree 0. Now our leading term is going to have the variable with the highest exponent. That's why they've labeled x squared. Okay? And they want the degree of this polynomial. The degree, you look at the largest number here. That's why they put degree 2. Okay? All right, let's look at the second example here. We have a -5 and a plus xy. So, I would like my terms. They've labeled them as a -5 and an xy. What is the coefficient of that xy? That's his degree. But what is the coefficient? The number in front. It's the only number that can never hide. Only 1. If you don't see it, there's a hidden 1 there. Let's say we have 1xy. Whenever we stick variables together, all we do is we basically create a triangle. We're creating a different object. Okay? Because when we deal with the other guys, constants are little baby squares. Okay? 2 variables create a triangle. If we have 1 variable, it's going to be a long rectangle. That's what the algebra tiles show us. So, the degree of any constants, 0 variables, 0 degree. Here I've got 2 variables, and both of them have a hidden 1 for an exponent. So they each have a little baby 1, and that's what was added to get the 2 for the degree. Okay? We had to add those 2 baby 1s up there. So now they've got degree 2. So our leading term, the leading term is the guy with the actual biggest degree. Well, if we've got a degree 0 and a degree 2 wins big time. So that means the leading term is actually the xy. It's always the variable ones. And the degree is going to be the degree of that. Okay? Highest degree always wins. And that, again, that's to name them. To give them their specific name. Okay. Are we ready to move on to the middle of your page? Is this making sense so far a little bit? Kind of. It'll make more sense once we actually get into practicing some questions. Okay? All right. Let's take a look at this one. It says, here are the names of different specific polynomials. As we discovered, monomial, 1 term. Okay? Binomial, 2 terms. Trinomial, 3 terms. And these are just showing you different examples of monomials, binomials, and trinomials. That's what they are. Okay? So, this is showing us a separation of 2 terms, 2 terms, 2 terms. Okay? That's what it's showing us. Now, which one, I would like to know the degree of, let's go the degree of this one right there. What is the degree of this top right one right there? What is my degree? Okay, show me your fingers. I want to see your fingers. Don't just look at Emily and decide. It's degree 2. How come? Variables are the ones that we name the degrees by. The 2, yes, he's 2 squared, but he's a coefficient. We don't use coefficient numbers as degree numbers. We would solve that coefficient. That's actually 4x squared. So, this part right here, that little 2, he's not part of naming our degree. This guy's degree is a degree 2. Okay? Because remember, only variables tell us degrees, not the constants or coefficients. All right. What about the degree on this guy? The one I circled up here in blue. What would his degree be? Show me your fingers. What do you think? Show me your fingers. What's the degree on that guy? It's a degree 2. Count the variables. They each have a hidden 1 on them. And if the variables are stuck together, you have to add them. Okay? But only if they're stuck together. So these guys on the bottom here, I would add a 1 on the A and a 1 on the Y. And this guy here would be a degree 2. So I've got degree 2, degree 2, degree 2. So since they're all degree 2s, you would put them alphabetically. So the a would go first, then the ay, then the y squared. Okay? Does that make sense? We're just talking about putting them alphabetically. Okay, so when you know what the degree is, and you're only looking at the letters for degree, okay? When you find their degree, you're just putting them in terms of who's bigger, who's smaller. Okay? All right, we're going to take a look at algebra tiles. So, we've got a couple different polynomials. They're telling us in your booklet, and it'll be for all of your quizzes and your booklets, but you need to make sure that you always check your legend. There should always be a legend. The legend tells you what color represents what object. So here they're saying shaded is positive, white is negative. That's what they're showing us. So unless they change it in any of the other instructions, this is the way it'll always be for your booklet. Okay? So they're showing us different representatives. So they're showing us a big square. Okay? If we see a big square, that means it's got a squared sign on it. So this one is always exponent 2. Here we've got degree 2, but it's with 2 different letters. Okay, so this guy's with 2 different variables. So, it's a rectangle, but what do you notice? It's definitely it's double the width of this long, skinny rectangle. So we call these long, skinny rectangles, sometimes we call them sticks. Okay, the long, skinny rectangles. Okay, and that way we can tell the difference between a stick and just a normal rectangle. So we've got squares, rectangles, sticks, and then which way are they pointing? If they're pointing up and down, it's an X. If they're pointing left and right, it's a Y. Okay? And then they're just showing us a teeny baby square. The teeny baby squares are the constants. These are the guys that are the lonely ones. So these guys are constants. Okay, tiny baby squares are the constants. Okay. So we're going to look at starting to draw some of these and what they look like when they're drawn. How are we doing so far? So? Yeah, you wait till you see what's going on though. It'll actually help. Okay. So we've got 2x2, a negative 3, and a positive 2. So you're going to notice, what did they pull out? Well, they showed you this. So we're going to match each part. So what they're showing us is this. That these little rectangles are going to match the negative 3x. Because remember, they're saying that x runs a vertical. Okay, so x is vertical. And they're also saying he is a long, skinny rectangle. So I have a long, skinny rectangle, 3 of them, and they have to be white, because it says white is going to be for negative. Shaded ones, okay, are the positives. So we've got 2 big squares, those are the x squared. We have 2 baby squares, that's the plus 2 constant. So we've got constants, and we've got variables, and we've got variables squared. Okay? Well, let's take a look at what it would look like the next way. Let's put this one down, let's put this guy up. So, we have a negative x squared. So this guy matches this guy, negative x squared. Okay? Remember, negative is white. That's why he's white. We have a negative 3 constants. That's our negative 3 constants. We're still dealing with the variable x. So since we're dealing with the variable x, our sticks are going to run straight up and down. We were dealing with y, we'd lay them down flat. Okay? So we have 2 of these guys. That means they're positive 2x right in the middle there. Okay? Now you're going to notice what they do is when they label a polynomial, they're going to make it go from highest exponent to lowest exponent to 0 degree. So basically from highest degree to no degree, which is why they've got x squared degree 2, x to the 1 degree 1, no variables, so no degree 0. So they will always be put in that way. That's called descending order of powers. Okay? So descending means they're getting smaller. All right. Let's look at the last example, example 3. So, example 3, we have some x's and some y's. And we see x, y together. Now, x and y together are a rectangle, but they're thicker rectangles. Okay, they're wider. They're like 2 of these x's together. So we've got our negative 2xy's. We've got them white ones. Those are our white rectangles. We've got our vertical x's. Those are vertical x's. And then we get our horizontal y's. And then we get our positive 1. Okay? He's the constant. Remember the constant are the t little squares. Okay. Like term. Dun, 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 dun. Top of your next page. What is a like term? Well, part of math is about matching things. Okay. Like terms. Like terms are when you take the same base and same exponent. So they need to have the same base and same exponent. And if they have the same base and same exponent, they are like terms. So, if we look at like terms in the charts, I will show you exactly what I'm talking about. So they have the same base and same exponent. That's how we know they're the same. Okay? So you can group apples together, oranges together. Okay? But not apples and oranges. They're different. That's the same as our x's and y's here. So, if I were to look at this first grouping, they each have an x, but what's more important is they each have x to the 1. Okay? If you look at the ones right beside them, how come they're not like terms? What's wrong with this set? What's wrong with that set? What do you notice is different? Yeah, their exponents are different. One's got a 2 and one's got a 1. They're not like terms if their exponents are different. Let's look at the next guy. One of them's positive, one of them's negative. Did like terms say anything about positives and negatives? No. So they can be positives or negatives. It doesn't matter. The thing that matters most is same base, same exponent. So they have to have the same base, meaning the variable, and the exponent in order to add the numbers in front. So these guys both have an x2, x2. That means they are like terms. Well, what's wrong with that set on the right-hand side? They both have a squared. What's wrong with them, Jay?
Different base.
Different base. They have different variables. So these guys have a different base, different variables. So that's why you cannot add them together. Okay? What about these guys? Why did they say they were like terms? The one that says xy and one that says yx. Look at our definition. Does the definition say anything about order being important? No. So as long as they still have the same letters and the same exponents, you can add them. And these guys each have x1, y1. x1, y1. They both have 1s on them, so you can add them together. They are considered like terms. Okay? So those guys are the same. Now, why can't I add the other guys together in the other side? What's wrong with that side? They both have y's. That's right. They both have a y, but then the other guys have an x, and the other guys have a z. The variables must be identical, and those ones are not. They only have one letter identical. They have to be identical in every way to be considered a like term. All right, the next one's on the bottom. You're noticing, who has the squared sign? The y. X has a 1. If you look at the guy right beside him, the y is a squared and the x has a 1. Because the variables match in every way, it doesn't matter the order they're written, they match in every way, so you can add them together, they're like terms. Whereas this guy right here, the exponents swapped. One guy has an x to the 1, one guy has an x to the 2. The other guy has a y1, the other guy has a y2. The wrong exponents on the wrong variable. So these guys do not match. Okay, the squared signs on different variables. Okay? So a lot of this polynomial business we're going to be dealing with is literally just matching things. Okay, so it's a lot of matching. So they're showing us on this one, you have these as well, x to the 1, y to the 1 is the same as y to the x. Remember, order isn't important. Doesn't matter who goes first. So you have these. Now, why are they telling us that that's what it gives us? We take a look. The first thing we're looking for is we are looking for the same base, same exponent. So when I look at these, when I would take my highlighter, and yes, I would use a highlighter, and I would go x squared, x squared, x squared. They're all the same. That means all I do is add the numbers in front. So I'm going to take 4 plus 3, subtract 2. So 7 subtract 2 is 5. And that's how they get their 5s. Okay? So as long as they have that same variable and the exponent, you can just add the digits in front. What part of the next one can be added? What part of example 5 can be added?
3 minus 2.
Good. Just the x squared parts can be added. Okay? Only the x squared part. Why are we not able to add the other guy? Yep.
Because its exponent is 1.
Exactly. His exponent is a 1. So we would add the 3 and the 2, and that's how they get the 1x squared. And then that 4x has nobody to add to. He's all by himself. Okay? On the bottom one. So we have a whole bunch that is the same. We're looking for the exponents. So we notice they all have xy's. Now we got to match exponents though. This guy has x1, y2. Looking for x1, y2. Well, that means this guy is going to match to that guy because they both have x1, y2. So I would have my 2 and my 1 is going to give me 3. That's how they got 3. So they grouped their like terms together. And then they got the 3 at the end there. It's positive 3. They took the other ones. They both had x squared and a y. They grouped them together. And then they added their numbers in front. They took 3 and subtracted 4. And that's how they got that negative 1 in front. Okay. All right, let's turn to, look at the very first page of your notes. There's a chart there. Okay, there's a chart there. Can I get everybody to look at the chart? I'm going to do an example above the chart of what I'd like you guys to do to fill in the chart. So, if I've got one that looks like this, 2xy plus 5y squared minus 3x cubed plus 4x squared y. Alright, so that's my example. I want the number of terms. So if I want the number of terms, that means I'm counting different things that are being separated by the plus signs and subtract signs. So that means if I were to take a look and circle them, I've got 1, 2, 3, 4 different terms. So in my term box, I put a 4. When it says list them, you would write them left to right in the order and put a comma between them. Okay? The degree, now you've got to look for the variables. And you got to look at those exponents and the variables. So for mine, I've got an x to the 3. He's bigger than a 2, and these two add to a 2. What does that one over here add to? These guys right there, what do they add to? 3. That's a degree 3 there. So I have 2 that are degree 3. How do I know who would go first? The one with only one variable goes first. So we put him first, then him second, if they wanted it written in order. Okay? So it is a degree 3, and I don't have a constant. So if I don't have a constant, I would say NA not applicable, I don't have one. Or you could write none. There is none. Okay? So I'll give you a few minutes. I want you to fill out the charts. Okay? Okay. Let's take a look at the last 3 examples here, guys. So we're going to go down in each column. Okay? Pay attention, please. We're moving down in each column. So you just want to count things that are being separated. So right here I've got 1, 2, 3 things being separated. Over here I've got 1, 2, 3 things being separated. Same thing. 1, 2, 3 things being separated. Okay, so for all 3 terms. Trinomials. You would list them all with commas. I'll let you guys do those on your own. We're going to do degree. I'm just going to erase all my circles down. Degree is the highest exponent on the variable. Now, if the variables are stuck together, then you add them. If they're not stuck together, you don't add them. So this guy up here, the highest one between a 2 and a 1 is 2. So this guy's degree is a 2. Over here, I've got a 5, a 4, and a 1. Who's bigger? 5. Over here, I've got a 2 and a 1. Who's bigger? 2. Good. All right, now we're going to go down into the constants. They're the ones that are lonely. Okay? So, don't forget you need to take the sign in front of them. What that's going to mean is it's going to tell us whether something's positive or negative. Okay? And that's going to matter when we add numbers together. So, this guy's a negative 8. Are there any constants on the third example? No, there are none. And on the last one, it's a negative 9. Okay? Make sure you have those listed, please. Okay, this concludes lesson 3.1.